Let's take a look at the reduction of order in general terms. What we have here is a differential equation, a second order differential equation of this form, and then we're going to assume that we have y1 as a solution, and we're interested in finding our second fundamental solution. And the way we'll do that is we will let y equal to u times y1, and that will help us find our fundamental solution. So what we need to do is we need to take some derivatives and replace it back into the original differential equation. So first, the derivative of y using the product rule will be the derivative of the first times the second plus the first times the derivative of the second. And now after that, we're going to take the derivative of this again to get y double prime, and then we will get the derivative of the first term, which is a product, times or plus the derivative of the second term, which is another product. And so what we want to do is replace our differential equation with the values or with the expressions that we found. So y double prime can get replaced with all that stuff in y double prime. Y prime can get replaced with all the stuff that we found for y prime. And then y is just u times y1. So what we're going to do is we're going to gather all the like terms somehow, and we're going to gather the like terms according to u. So u prime or u double prime only has one term. U prime has a few terms, and then there's u that has 3 terms. So after we collect all those terms, gather all those terms, collect it, put it together, and in this process I also ended up factoring out when there's more than one term, we factored out the u's. So the u prime got factored out, and then we have these two y1 primes, and then this p times y1 had a u prime. And then all the factors with a u ended up here. Now, if you take a look at that, that is exactly, oops, I think this is just y. If we take a look at that, that's exactly our differential equation. And if we said that y1 is a solution to the differential equation, then if we put y1 into the differential equation, it should equal to 0. And in fact, that's what happens. This whole thing will disappear. So let's make this disappear. And then this is now our new differential equation. Now, we can solve for this differential equation. I think it would be better looking if we actually did another u substitution. And the substitution is that we'll let u prime equal to w, so that u double prime is equal to w prime. And now we have a differential equation that's a first order differential equation. It's linear. And in fact, in this particular scenario, it's actually separable. We can start seeing the separable differential equation by first dividing by y1. So if we divide by y1, this will have a 2y prime 1 divided by y1, and this will have a py1 divided by y1, and that will just leave us with p. And the other thing I did in this particular step is I rewrote w prime to be dw dx, and that will help us perform the separation. So this is in fact a separable differential equation. We can bring this w times this thing in the parentheses over to the other side, and then divide by w, and then multiply by dx. And so we will have this equation and then everything here, remember that y1 is a specific function and it's a function of x, and p is also a function of x, and w is the other variable. So y1 in this case is no longer a variable, it's a specific function that we found because we said that it was one of the solutions. So now what we're going to do is we're going to integrate both sides, and the left hand side is pretty clear, that's the ln of w. The right hand side has two terms, the integral of p, I don't think you can simplify, but let's focus on the integral of this. If we take a look at that and do a u substitution, or some sort of substitution, if we let u equal to y1, then the derivative of that is y prime 1, and that would cancel. And so this will end up being the ln function. So the derivative, or the integral of both sides, will give us an ln of w on this side, and then taking out the minus 2, we get the ln of y, and then here the negative sign, and the p will give negative p, the integral of negative p with respect to x. So what I'm going to do in this case is I'm going to bring this term to the other side so I can find a way to combine the w's, or combine the ln functions, because we're interested in solving for w, and then there's an ln in there. So let's bring this over to the other side, and I'll do that by just doing some cutting and pasting. And then now if I bring this 2 as a power of y1, I have ln of w plus ln of y1 squared, and I can combine that into one ln. So just a few log properties will get us going with our next step. To help us solve for w, and to do that we're going to take the e of both sides, or raise both sides to the power of e, and then we're going to simplify the left hand side so that it's just w times y1 squared, e to this power, and then to continue to solve for w, I divided both sides by y1 squared, and so this is the expression that we have for w. After that, we want to remember that w was actually equal to u prime, and we're interested in finding u prime. So remember that this is equal to u prime, and to find u, we're going to integrate both sides, and so the integral of u prime is just going to be u, and then the integral of the right hand side, well, can't really simplify it because you don't know what p is, you don't know what y1 is, and so this is all we have right now. And then finally, remember that the whole reason for finding this is to multiply this by y1 so that we can have your y2, your second your second solution. So this is our original substitution. Our y2 is equal to u times y1, which is y1 times u, and u is that expression that we just found, which is this big messy integral. Okay, so there's a couple of things that we should probably note. We have two integrals that are happening here, so really when you integrate this, you're going to get a couple of constants. But these constants will be factored into our general solution, so we don't need to worry about that. And then so the big summary is the formula that if we have y1 as a solution to our differential equation, then we can get y2 by just using this formula. Okay, so it looks like a messy formula, but it's actually not that bad, and it'll help us solve for some of the differential equations that we're going to need, and we should be able to solve for it rather quickly. Let's do an example. And for an example, let's take this differential equation that we worked on in class. We got x squared y double prime plus 5xy prime plus 4y is equal to 0. And then we're going to assume that we have a solution that's x to the negative 2 power. For this to work, we want to rewrite our differential equation so that it's y double prime plus p x times y prime plus q x times y is equal to 0. So now let's identify the players here. We have y1 is equal to x to the negative 2, and p is going to equal to 5. That's 5 over x. So if I were to just copy this and fill in the blanks, the blanks are y1. So y1 is this term, and then we have y1 squared is that term, and then p of x is 5 over x, and then we should be good to go. So working within the integral, we can work this out first. We have e well, the negative 5 can come out, so that's just the 1 over x, and then we have 1 over x, and then the integral of 1 over x is ln x. And then now we have this property again where the 5 can become a power of x. So if we put that as a power of x, then we're allowing the e and the ln to undo each other, and so that's just going to be x to the 5th in the numerator, and then x to the 5th in the numerator divided by x to the 4th in the denominator will give us x to the negative 1. That's just 1 over x. So the integral of that is ln x. And so our final result here should be x to the negative 2 power times ln x. Okay, so I believe that's what some of you guys got as you're working with this. So now let's take a look at our second example. And we'll start off again using that formula. We'll start off with y1 is e to the negative 4x, so that's the y1 that goes in here. It also goes in here. And then our p is 8, and so that goes into the formula as e to the negative integral of p dx. Well, that just turns out to be e to the negative 8x. So if we put that there, e to the negative 8x, that's just equal to 1, and the integral of 1 is just x. So here we have it. This is our second solution. Now you can verify that the second solution is linearly independent from the first solution by using Wronskian. You can also do that over here. This is the first solution or second solution is that times ln x. And then once you verify that, you can see that they're linearly independent. And so then you have these solutions. So our first solution is y. Y is going to equal to c sub 1 times our first solution plus c sub 2 times our second solution. And that's the general solution for our first differential equation. Now our second differential equation has a solution that's kind of similar to this. So I'm just going to copy and paste this and change our function. So our y1 has changed to e to the minus 4x. And then our y2 is going to be e to the minus 4x times x. Okay, so once you have the formula down, you can get these solutions a lot quicker than what you guys had to do in class, but I think it's worth it to go through the formula, the algorithm for the reduction of order. And then once you do that, then if you can get used to this function, then you're good to go. All right, hope that helps.